You will be able to solve complex exponential equations by using the properties of exponents and a clever technique called substitution. By the end of this lesson, you'll be comfortable handling equations like the ones we'll see today. Before we tackle complex equations, let's refresh our memory on some key properties of exponents that will be essential for our work today. First, the multiplication property tells us that when multiplying powers with the same base, we add the exponents. This means that a to the power of m times a to the power of n equals a to the power of m plus n. The division property is the opposite. We subtract the exponents. This means that a to the power of m divided by a to the power of n equals a to the power of m minus n. So again, to repeat, to divide powers with the same base, you subtract the exponents. Finally, the power of a power property states that to raise a power to another power, we multiply the exponents. So a to the power of m, all raised to the power of n, is equal to a to the power of m times n. This means amcn.net. Memorizing these three properties will be a great help in solving these problems. Now let's look at a common and very powerful technique for solving these kinds of equations. Substitution. When an equation becomes too complicated to solve directly, we can sometimes simplify it by replacing a complex expression with a single variable. This method is called solving by substitution. It involves a simple three-step process. First, you identify a repeated part of the equation and substitute it with a new variable, like u. This first step is the most crucial. Choose what to substitute. For example, if you see 4 to the power of x in your equation, you might let u equal 2 to the power of x because 4 is 2 squared. Second, you rewrite the original equation entirely in terms of your new variable, u. This should make the equation much simpler, often turning it into a standard quadratic equation. Your new equation should be easier to solve. For instance, if you substituted u for 2 to the x, then 4 to the x becomes u squared. Third and finally, once you've solved for u, you substitute back the original expression to find the value of the main variable, x. Don't forget this final step, as u is just a placeholder to help you find x. In our example, if we found that u equals 8, we would substitute back and solve 2 to the power of x equals 8 to find the value of x. All right, let's put these ideas into practice with our first problem. The equation is 3 to the power of x plus 2 plus 3 to the power of x plus 1 equals 162. Notice how the exponents are sums. This is a great indicator that we should use our multiplication property of exponents, which says that a to the power of m plus n equals a to the m times a to the n. So we can rewrite the equation. The first term, 3 to the x plus 2, becomes 3 to the x times 3 to the 2. The second term, 3 to the x plus 1, becomes 3 to the x times 3 to the 1. So the equation is 3 to the x times 3 squared plus 3 to the x times 3 to the first equals 162. Now let's simplify the constant parts. 3 squared is 9, and 3 to the first is 3. So we have 9 times 3 to the x plus 3 times 3 to the x equals 162. Do you see a pattern here? We have 3 to the x appearing in both terms. This is a perfect opportunity for a substitution. Following our substitution strategy, let's make the equation simpler by substituting for the common term. We will let u equal 3 to the power of x. This is the expression that is repeated in our simplified equation. Now we replace every instance of 3 to the x with our new variable, u. The equation becomes 9 times u plus 3 times u equals 162. Look how much simpler this is. This is now just a linear equation in u. Combining the terms on the left side, we get 12u. So 12u equals 162. To isolate u, we divide both sides by 12. U equals 162 divided by 12, which simplifies to 27 over 2. This is our solution for u, but remember, we're not done yet. We need to find x. We've found the value of u, but our original problem asks for x. This is where our final step, the substitution back, comes in. Recall that we defined u as 3 to the power of x. We just found that u equals to 7 over 2. Setting them equal, we get 3 to the x equals 27 over 2. How do we solve this? We need to use logarithms. Specifically, we can take the logarithm of both sides. It's often easiest to use the natural logarithm denoted by ln. So we have the natural log of 3 to the x equals the natural log of 7 over 2. Using a key property of logarithms, we can bring the exponent x down in front. This gives us x times the natural log of 3 equals the natural log of 27 over 2. Now, to isolate x, we just need to divide both sides by the natural log of 3. Our final answer is x equals the natural log of 27 over 2 divided by the natural log of 3. We could also write this using a change of base formula as x equals log base 3 of 27 over 2. Either form is perfectly correct. Let's move on to our second problem to see another variation of this technique. This time, the equation is 2 to the power of x plus 2 to the power of x plus 2 equals 40. Again, we see a sum in the exponent, so our first step is to use the exponent multiplication property to separate the terms. Remember, a to the m plus n is a to the m times a to the n. Applying this, the equation becomes 2 to the x plus 2 to the x times 2 squared equals 40. Now let's simplify that constant term 2 squared, which is 4. Our equation is 2 to the x plus 4 times 2 to the x equals 40. Notice how 2 to the x appears in both terms. This repetition signals that substitution will work perfectly. We will let our placeholder variable u be equal to 2 to the power of x. Substituting u into the equation gives us u plus 4u equals 40, which simplifies to 5u equals 40. Dividing by 5, we find that u equals 8. We have the value for u. Now for the final step, substitute back to solve for x. Since u equals 2 to the x, we can write 8 equals 2 to the x. Can you see the answer here? We need to express 8 as a power of 2. Since 8 is 2 times 2 times 2, or 2 to the third power, we have 2 to the third equals 2 to the x. When the bases are the same, the exponents must be equal. Therefore, x equals 3. This time, we didn't even need logarithms. The answer was a simple whole number. Let's try one more example to solidify the process. This time, we'll encounter a quadratic equation. Consider the equation 4 to the power of x plus 2 equals 3 times 2 to the power of x. This looks a bit different. Notice how one base is 4 and the other is 2. We know that 4 can be written as 2 squared. Let's use this to rewrite the first term. So, 4 to the x becomes 2 squared to the x, which is the same as 2 to the power of 2x. Our equation is now 2 to the 2x plus 2 equals 3 times 2 to the x. We can write 2 to the 2x as 2 to the x squared. This reveals a clear substitution. Let's rearrange it into a more standard form. Subtract 3 times 2 to the x from both sides to get 2 to the x squared minus 3 times 2 to the x plus 2 equals 0. Let's define our substitution. We'll set u equal to 2 to the power of x. Now we substitute u into the equation. This gives us the quadratic equation u squared minus 3u plus 2 equals 0. We can solve this by factoring. It factors into u minus 1 times u minus 2 equals 0. Setting each factor to 0 gives us two possible solutions for u. U equals 1 or u equals 2. We have two potential solutions for u, which means we have two potential solutions for x. We must substitute back for both. First, let's take u equals 1. Substituting back our original expression for u, we get 2 to the x equals 1. Any non-zero number raised to the power of 0 equals 1, so x must be 0. Next, let's take u equals 2. Substituting back, we get 2 to the x equals 2. The only way for this equation to be true is if the exponents are equal. So, x must be 1. Therefore, the original equation has two solutions. X equals 0 and x equals 1. This shows how substitution can reveal multiple answers. So, let's recap what we've learned today. We've seen how to solve more complex exponential equations that don't have the same base on both sides. The main strategy is a powerful two-step dance. First, use exponent properties to rewrite the equation so that the base is separated from the exponent that contains the variable. Look for common exponential terms. Second, use the U substitution method to replace this common term. This simplifies the equation to a standard algebraic form, often a linear or quadratic equation. You solve for U, and then don't forget to substitute back and solve for the original variable, x, which may require using logarithms. This method is a fantastic way to turn a challenging problem into a series of familiar steps. Keep practicing, and you'll become an expert in solving these kinds of equations.